Section 5.1, now we're into chapter 5. Chapter 5 is all about exponential and logarithmic functions. Technically, you were supposed to have learned about exponential and log functions back in college algebra. This is part of your prereq, or almost, actually, I would say half of this chapter is material you should have covered already in college algebra. That being said, it does not mean that students don't struggle with this material in this class. They do. It is what it is. So if your background knowledge on exponential and logarithmic functions is weak, then you need to pay special attention to the first two sections where we're basically just going to be reviewing information from college algebra. So section 1, we're going to talk about exponential functions. In section 2, we'll talk about log functions. And then in sections 4 and 5, we'll talk about the derivatives of both of those respectively. We skip section 3, it's not required for our class, and then we'll do some applications in section 6. So really that's only 5 sections for chapter 5, which is why it doesn't take up a whole lot of space on our schedule for our class. So let's talk about exponential functions. Today we're going to simplify them, we're going to graph them, and we're going to evaluate them. I'm not as keen on the graphing, although I do think a lot of times when we're trying to find function values, it's really good that we have an understanding of what the graph looks like. So we will touch on it a bit. So as you can see here, we have a situation where we have exponential growth versus linear growth going on in this coordinate grid. You have 3 different functions. The first function is linear. It's f of x equals 2x. This is the kind of function that we deal with all the time. We learned about it a long time ago. X squared is another one you should be really familiar with. And then the last one is 2 to the x. I apologize. These came out a little bit blurry. It's not just what you're seeing on my video. These are, and your notes will be blurry. So I don't know why. All right. So 2 to the x is what g of x is. You can see that these graphs are put here to the right, and you can compare the values and look at the shape of the graph. But the function f is your linear function, 2x. Notice that you just have this straight line. Your function h is quadratic. It's a little bit hard to tell based on this scale, but it's, you know, we're just seeing your half of this parabola. It's definitely curving upwards. It's just not doing so as quickly. Then the function g, you can see, starts to increase, and it increases pretty slowly so that it seems to follow the growth rate of the function h, but then it veers off for values where x starts to get really large. So as x gets to be a larger value, g of x gets really large very quickly. And that's the whole idea behind putting the scale to these numbers. The function g is going to become so large for these values of x that we need to include more values on the y-axis just to get a sense of what the graph actually looks like. But yeah, so that's how we could compare these graphs. Exponential growth happens very rapidly, so our function g is going to be growing much more quickly as x gets larger. And it doesn't even have to get that large. I mean, we're talking about 7. So 7's not a big number, but 2 to the 7th is a big number. If you don't remember, when you're taking 2 to a value, I mean, when 2 is the base, you're just taking that number to that power. So, you know, 2 to the first is 2. 2 to the second is 2 squared, which is 4. And then so on and so forth. So 2 to the third then is 8. Oh, you know what? I forgot 2 to the 0. Any power, any number, any real number to the 0 power is 1. That's where this 1 comes from. So 2 to the 0 was 1. 2 to the first is 2. Maybe I should put these x values here. So x equals 0, x equals 1, x equals 2, so on and so forth. But these all correspond to the given y values. And of course, when x equals 3, we're talking about 2 cubed, which is 8, all the way down to x equals 7, which gets you 2 to the 7th, which is 2 times 2 times 2 times 2 times 2 times 2 times 2. So that's what you're doing here with these values. Linear functions grow at a constant or additive rate of change. Exponential functions grow by a constant multiplicative factor. Okay, so for the linear function, you just have this constant rise over run value that's occurring, whereas for the exponential functions, you're just constantly multiplying by that same value over and over again. All right, what do we have next? Evaluate. These evaluate problems, even though you should have done these already in algebra, are so crucially important because we're going to end up here with some derivatives where we're going to have to be able to simplify these exponential expressions using rules for exponents. So let's start out with one that's a little bit more basic. So this will be -2 to the third power. Now the negative 2 in that case is in parentheses, times 2 to the negative third. And in that case, the 2 is not in parentheses. Not really going to make a difference there. But actually here, long story, it doesn't make a difference here either because the 3 is an odd power. So we know that if we take a negative number to an odd power, we don't require the parentheses. It's not going to make a difference. It's only when the power is even. And then we'll take in the denominator -8 to the 2/3 power. I'll show you how to simplify that. Times 16 to the -1/2 power. So there's a lot going on here. The goal here is to use exponent rules to simplify, but also just to rewrite this in a way that we can evaluate this to just a number by the time we're done. So one of the first things that I would do would be to take some of these negative exponents and make them positive. And then anything that I can simplify right away, I might go ahead and try to simplify it. Like for instance, I know what a 1/2 power is. When I move that up to the numerator, I can simplify that power. So let's first rewrite this just by making all the powers positive. Now, I don't want you to feel like, wait, I did this way instead. Does that mean that what I did was wrong? There are a lot of different ways of approaching these problems, and a lot of these steps you can switch the order for. So I don't want you to feel like if you did something in a different order that you did it wrong. So I just have chosen to make my exponents positive first. So the -2 to the third power, we can keep. If you wanted to simplify that right away, you could also do that. I'm going to move this 2 to the -3rd power into the denominator, and now it's 2 to the +3rd power. So just moved it down there. As far as the -8 to the 2/3, it's a +2/3 power, so I'm going to leave it. And then for 16 to the -1/2, I'm going to move it into the numerator as 16 to the +1/2. Now I'm going to rewrite some of these values. For instance, I can go ahead and simplify the exponential expressions where we have these cubed values. I'm going to do that now. And then we can rewrite 16 to the 1/2 as the square root of 16. And then we can also rewrite -8 to the 2/3 power. So don't feel like, oh, wait, I forgot my calculator. First of all, you should not have to worry about that because you're at home. Maybe you're at home watching this video. I don't know where you are, but I'm going to show you how to simplify it without a calculator. All right, -2 to the 3rd power is -2 times -2 times -2. It's going to stay negative because you have an odd number of negative signs, and 2 to the 3rd power is 8. So -2 to the 3rd power is going to be -8. And then we have the square root of 16. And then 2 to the 3rd power is +8. And then -8 to the 2/3. Remember that we said that if you have a rational exponent, the denominator is going to be the index of your radical, and the numerator is going to be the power on your expression. So what we really have here is the cubed root of -8 squared. We also said that it does not matter the order in which you place this exponent. You can place it outside of the radical or you can place it inside. And I'm kind of thinking that outside might be better. And mine sort of looks ambiguous. I'm going to move it a little bit. So I'm going to take the cube root of -8 and square it. If this cube root of -8 is bothering you, remember that we can take an odd root of a negative number, just not an even root. So I can't take the square root of -8, but I can take the cube root because I know of a value that when I cube it, it gets me to -8, and that value is -2. Let's go ahead and simplify. One thing you might want to do right away, just to get some things out of the way here, is just to cancel out these 8s. They're common factors. We're multiplying. We have 8/8, which we can simplify to 1. So if you want to go ahead and rename 8/8 as 1/1, that gives you a little bit less to look at. And now we can just go ahead and evaluate what's left over. The square root of 16 is 4. Don't forget your negative sign. And then in the denominator, we have the cubed root of -8, which is -2. And we're going to spare it. The cubed root of -8, you can put this in your calculator, but remember it's -8 to the 1/3 power. Since students tend to ask me, I'm going to show you how to get a cube root in your calculator. So you hit the math button, which is right here, and you go down to number 4. That gets you a cube root. I mean, if you have to use your calculator, fine. It's available to you. I just prefer that you know how to do something like that by hand, but it's there in case you need it. All right, so the cube root of -8 is -2, and that whole quantity is in parentheses. That's going to get squared. So we have -4 over -2 times -2, which is +4. And our fraction simplifies to -1. And just to give you a sense for the many different ways in which you can do these problems, when I did this with my class last semester, it's funny because I'm looking at the notes now, I did it in a completely different way. So, I mean, I had this done, and I mean, I got the same answer in the end. I still got -1. It was just done in a very different way. I think I started out the same, and then I don't know. But my point is, there are a lot of different ways to approach these to still get the same answer, and not by coincidence, because not all these steps have to be done in that specific order. So that's kind of the nice thing here, is you have a little bit of choice as long as you are using the right properties. Okay, so the next one is going to be, this one's a little bit longer. I'm going to have to kind of stash this in here. Sorry. 3x cubed, and this is a whole quantity, by the way, that's going to be taken to a power. So 3x cubed y to the -2nd z to the 0 divided by y to the 3/2 z to the -1/2, and that whole expression is being taken to the -2nd power. Now, the first thing that I would do for a problem like this is this whole -2nd power thing, I don't like. Now, you have a couple of options. You could start by distributing this exponent, because you're taking an expression to a power that just has multiplication inside of it. When you take power to a power, you multiply the powers, and this is just a product to a power. You could multiply this exponent into every single one of these expressions if you'd like. What I'm going to do to start out, though, is probably just simplify what's inside the parentheses. That's the approach that I'm going to take. So to do that, I first want to just rewrite everything and take it to the +2nd power. I'm getting ahead of myself here, saying one thing and writing another. Okay, so I'm going to take my expression and rewrite it to the +2nd power. In order to do that, I need to take the reciprocal in the numerator and the denominator. If I had to formalize that into a rule, it would be this. A over B to the negative m is b over a to the positive m. This is a rule that you should have learned in algebra. What it says is that you can take what's inside your quotient, you can take its reciprocal, and then change the sign on your power. I know, so many obscure rules. If you don't remember them, that's fine. We're going to hit all of them. So there shouldn't be anything where it's like, how would I have known that? I've never seen this. We're gonna go through all of them. So we have y to the 3/2 power. I'm gonna do everything in separate steps here. There's a lot going on. Z to the negative half, because you know I wanted to move its position in the fraction, but remember all this is being taken to the positive second power. So I'm just switching the numerator and denominator because I can do that with negative exponents. And then in the denominator, I have 3x cubed y to the negative second. Now, z to the 0 power is 1. So I'm going to go ahead and evaluate that. I'm going to write it just so that you know I didn't just forget about it, but I'm not going to keep rewriting that. So when you take any real number to a power, to a 0 power, you get 1. Okay. Now, everything's being taken to a positive exponent. That's good. What I'm going to do now is I'm going to simplify like I did the last one inside the parentheses. And again, it's up to you if you want to distribute the exponent in right now. I'm going to simplify what's inside the parentheses. So for instance, I'm going to pull this y to the negative second into the numerator as y to the positive second. And I'm going to bring z to the negative half down to the denominator as z to the positive half. So I'm going to do that now. So I have y to the 3/2 times y to the positive second. And then I have 3x cubed times z to the positive half. All right, I'm going to take this entire quantity to the second power. And then I'm going to go ahead and simplify in the numerator. Remember when you're taking, when you're multiplying with the same base, you add the exponents. So what this really looked like in the numerator is y to the 3/2 plus 2 power. So we can simplify that. So 3/2 plus 2 is 1.5 plus 2, which is 3.5, or 7/2. 3/2 plus 4/2 is 7/2. So we'll rewrite this again. So we have y to the 7/2 divided by 3x cubed, z to the 1/2, and that whole thing is being taken to the second power. Now to simplify, what I'm going to do now is I'm going to apply that rule where I'm taking a product and a quotient to a power. So I'm going to go through and distribute that power. If I can summarize what that looks like, it's like if you have a times b to the m, it's a to the m times b to the m. So that would be the rule that I'm going to be applying here in the numerator and the denominator. So now I can say that we have y to the 7/2 times 2 divided by 3x cubed. Now, I have to be really careful here because when I apply this exponent to the 3x cubed, I need to make sure that it gets applied to the whole quantity. So if you want to just apply it separately, that's fine. I'm going to apply it to the whole thing and simplify it in the next step. And then I have z to the 1/2 times 2. And we just have one more step. It's almost done. So 7/2 times 2 is 7. 3x cubed squared means I'm taking 3x cubed times 3x cubed. So 3 squared is 9. And then for the x's, when I take a power to a power, multiply the powers. So I have 9x to the 6th. And then z to the 1/2 times 2, which is z to the first. And that's what we end up with here for number 2. A lot of steps here for these algebra problems. And yes, I'm saying they're algebra problems because this is the type of thing that you did back in algebra. And it was hard when you had it then too, because there are a lot of rules. And even though there are a lot of times different orders in which you can apply these rules, you have to use the rules. So you can't just do whatever you want, and you have to be very careful to make sure that you're using the rules correctly. That's how we simplify. You're going to see some of those on your homework to work with. Hopefully they won't give you too much trouble because it is technically review, but I know maybe it's been a while since we've seen these rules. Students always struggle with them. So if you feel like you're struggling with exponent rules and you're like, oh my gosh, this is algebra, I can't believe I'm struggling with it. It's a very common thing for students to struggle with exponent rules. It's just one of those things you have to practice. Graphs of exponential functions. Okay, so this is what the graph of an exponential function will look like if we're talking about f of x equals a to the x. Now, a is just going to be some real number. In the first example that we talked about in the class, it was 2 to the x. So we had a equals 2. And we saw, remember that graph on the first page? Remind you of what it looks like. We had this graph heading upwards like that. That's because in that case we had a equals 2 to the x. All right, so in this case, a is positive. Your graph is just going to go up and to the right. So as x gets larger, the y value is going to get larger. But you're always going to have this y-intercept at 0, 1. And that's because if x is 0, when you take a real number to a 0 power, it evaluates to 1. That's why. Now, notice, though, that for these values of x that are smaller, your expression actually heads down towards, or your graph actually heads down towards the negative x-axis, towards y equals 0. Now, if we're talking about a value of a between 0 and 1, so some sort of fraction between 0 and 1, like maybe f of x equals like 1/2 to the x, in that case, your graph is going to go down from left to right. And for the same reason, you can pop in some values and see what happens. This is a little bit easier to see when we're talking about a real number and not just something like a, where we can't really test some values. But again, you're going to have the same intercept. It's just that depending on the values you use, the values for f of x are going to change just due to the way the exponent is going to work with your whatever numbers you're inputting. This is the general shape of the graph. Notice that both of these are going to have horizontal asymptotes at y equals 0. Both of them. It's important to remember for us, especially as we are going to be working on some derivatives, critical numbers. It's going to be really important for us to know where these asymptotes are on the graph. All right, so we're going to graph a little bit. I don't want to spend a ton of time graphing these because it is review and it is something you could technically input into your calculator. But I think it's important to look at a couple of these graphs. So if you think, for instance, about, let's think about this in terms of the transformations that would occur to your function. So we're talking about a base of 2/5. So in this case, you would say that a equals 2/5 if you're comparing it to the above, like, general view of what these graphs would look like. So, it would be this case because 2/5 is between 0 and 1. So that's what you'd be looking at for the general shape of this graph. Now, let's say for a second we just wanted to graph a different function. Let's say it was f of x equals 2/5 to the x. Usually we put parentheses around that just so it's really clear exactly what the base is. We don't want to think it's 2 to the x divided by 5. It's 2/5 to the x power. Now, if I was going to graph this function, I know what it's supposed to look like. I know the general shape. Let's say we let x be 0, for instance. If x equals 0, well, 2/5 to the 0 is 1. All right, so 2/5 to the 0 is 1. If you don't believe me, put it into your calculator. So if x is 0, y is 1, that gives us a point here on the function f. This is not the function g. This is our function f. I'm going to show you how g is built off of f. If I let x be 1, then y is going to be 2/5 to the first power. So if x is 1, y equals 2/5, which is like about exactly 0.4. So it's going to be about right here. Now we know that this graph is going to have a horizontal asymptote at y equals 0. So we know what it's going to do. So we know it's going to go down like this as it approaches the positive x-axis, but it's never going to touch. This is f, and we need to graph the other side of it. If you were trying to figure out, well, how would I get another point? Well, let's say let x be -1. In that case, y would be 2/5 to the -1st, which is the reciprocal 5/2. So that's 2.5. So if x was -1, you would have y here at about 2.5. You get this point, and this is what your graph would look like. Now you can double check that in your calculator, but if I was going to graph our function f, the function is 2/5 to the x. I'm going to zoom 6. And that's what it looks like. I would say be careful to try to make it look like you have this horizontal asymptote here. But this is what your standard graph would look like here for a base of 2/5. Now, what we're doing for g is a couple of different transformations. If you don't remember this from college algebra, it's probably going to be beneficial for you to spend some time remembering what these transformations are, look them up, practice a couple of them. You'll see some of this graphing a little bit on your homework. When you are adding, so instead of just 2/5 to the x, we have 2/5 to the x plus 1. You're adding inside the exponent, or inside, I want to say, inside the function, you're actually moving to the left. So when you have 2/5 to the x plus 1, your graph is getting shifted to the left 1 unit. Remember that if you were adding 1 outside of the function, it would shift it up. But since you're inside the function, you're actually going left, not right. And then the negative sign gives you an x-axis reflection. So that's going to take all of the values that you graphed and reflect them about the x-axis. So let's go ahead. If you would like, you can plug in some values, but the whole point here is just to be able to use the transformations to graph your function. So if I was going to move left and then reflect about my axis, let's see, moving to the left 1 unit and then reflecting about my axis. I don't know. I actually, sometimes students, and I know this because I always have to think about which way I'm performing the transformations. I would say double check with the transformation, but just plot some values because you know what the graph is supposed to look like. So if I was looking at my function g, what I'm looking to do is just use similar values here, but then just make the adjustments to the y value. But I'm going to choose similar x's. So, for instance, a value of x that I might make this like a colon here. A value of x that would work for me here might be something like x equals -1, because -1 plus 1 gets me to 0. And I like to have 0 because that will get me a nice point on the graph, because I know that if I'm going to take a number to the 0 power, then I'm just going to get 1. Well, in this case, I'm going to say that y equals negative and then 2/5 to the 0 power, which is -1. See how that works? So if x is -1, y is also -1. And I have this graph or this point down here. And then maybe choose another value of x, something like x equals 0 would be a good one, because 0 plus 1 is 1. So that just means that I have negative 2/5. So if x is 0, y is negative 2/5, which is negative 0.4, which is about here. And then you want to really be able to show this shape. Remember what you're expecting here is that you're shifting left 1 and then reflecting about the x-axis. So you know that you're expecting this graph to look sort of, I don't want to say reverse, but reflected. So you maybe get one more point over here. So I would say maybe let x be negative 2 and then see what you end up with. If that's the case, then you'll have y equals negative and then 2/5 to the negative 2 plus 1 is negative 1, which is just going to be negative 5/2. So if x is negative 2, y equals negative 2.5, which is about right there on your graph. So you're going to get this graph that heads down like this and also approaches the x-axis at an asymptote of y equals 0. We can also graph this in our calculators. So I'll label this G. But you can see how it was shifted to the left 1 and it was reflected about the x-axis. So if you're trying to figure out how you would shift this point right here at 0, 1 would move to the left 1, and then it reflects about the x-axis. It hops over the x-axis and it ends up here. So every one of these points is accounted for. So we had a point here at negative 1, 2.5. Well, we move it to the left 1 and we reflect it, and there it is. We had another point that was at 1, 2/5. Well, we move it to the left 1 and it hops down over the x-axis. So you can see that reflection and shift. So now we put this all together. I can say this is negative, don't forget your parentheses, 2/5 to the x plus 1. When we graph it, we can see that bottom graph. So it's really important that we understand what the graph is supposed to look like and that we have a general shape, because then we don't need to sit here and plot so many points. We just need to plot the most important ones. So the important ones, I would say, are the ones that end up giving you a 0 exponent. We found those in both cases, so that you can get that intercept. And then just a couple of points around that so you can get a good general shape of the graph. If the only thing I did here was plug in x equals 4, x equals 5, x equals 6, that would tell me nothing. You'd be like, okay, well, where does the graph like turn? What's happening here? Where do the values start to shift? So it's really important to choose the right values of x for which to evaluate this. So hopefully this sort of gives you a guideline for what you're looking for in that case. So you're looking for that 0 exponent and then maybe one on each side of the 0 exponent. And the 0 exponent doesn't always mean 0, because if you've got shifts going on, that 0 exponent could come from a different x value. All right, as far as other graphs here, like I said, I don't want to spend a ton of time on graphing, but we should at least just mention the transformations that are occurring with the graph. We already have a picture of 2 to the x. I'll just list out the transformations, and if you want to double check them, that's fine. But like I said, it's not going to be a very huge emphasis for me. I really think it's important that we know a general sense of what the graphs look like. But as far as being able to do all this algebra work on them, it's not a huge emphasis for this class. So if F is your base graph, G is going to be a steeper graph. So G is going to be a vertical stretch by a factor of 3. So what this means is the graph is going to just rise much more rapidly. So whatever this value is, it's getting multiplied by 3. For those larger values of x, the graph is going to increase even faster. And for 1/3, this is going to be a vertical shrink. It's going to shrink by 3 units, or stretch by 1/3, shrink by 3. So this means the values will not grow as quickly. So if we're talking about 2 to the x, so this one's going to be steep. This one's going to be shallow. So you would have your base graph of 2 to the x. When x is 0, y equals 1. When x is 1, y equals 2. When x is -1, y equals 1/2. So your general graph, let's see, 2 squared is 4. This is just a repeat of the graph from the previous page. Generating some values. So if this is y equals 2 to the x, kind of like that, what you would get here for g is just that these values are going to rise much more rapidly. So this value, when x equals 0, is not going to change. Well, actually, never mind, it will change. When x is 0, we have y equals 3 times 2 to the 0, and 2 to the 0 is 1. So our value of y is going to be 3 in that case. But you're going to see how all of these values would change. We can actually look at these on our graphing calculators. So let's see, you have 2 to the x. So this is the base graph that we have. And then if we have, whoops, is it ready? All right, 3 times 2 to the x. Be careful here with how you enter this. So your calculator is going to know to use the exponent before it multiplies. So make sure you're not using parentheses there. Otherwise, it'll think you mean 6 to the x when you don't mean 6 to the x. And that's where you can see that these points start to shift much more rapidly. So this value that we just found actually occurs here. And you're seeing these values just go up a whole lot faster. So if we chose x equals 1, for instance, we'd have y equals 3 times 2, we'd get 6. And you see how this graph just gets larger a whole lot faster. If we had x equals -1, 2 to the negative first is 1/2. So it's 1.5. So -1, 1.5 is about right here. So your function g, oh, this is not the best g I've ever graphed, but that's okay. You do the best you can. It looks more like that. It's terrible. Sorry, I'm not going to wipe it out and redo it, but you can make it look really nice. And then for the last one, you can see that this value for y is going to increase less rapidly. So we would say, here, maybe I'll just undo that. We have 1/3, so 1/3 times 2 to the x. You can see how, all right, here's our base graph, 2 to the x. And this one is h. It's growing a lot more slowly. So for our graph of h, when x equals 0, y is 1/3. And then you can check these with the table in your graphing calculator, but that gives you a y-intercept that's down here at 1/3. And then if x equals 1, then you just have y equals, well, 1/3 times 2, which is 2/3. So still not even up to 1 yet. Now you can kind of see how the behavior of the graph is changing. When x equals -1, the y is 1/3 times 1/2, which is 1/6. So super, super small. What happens at 2? If x is 2, y is 1/3 times 4, which is 4/3. So like 1 and 1/3. So again, still just climbing, but slowly. So this would be h of x. But notice that these graphs all still have the same shape. They all have the same behavior. It's just that one of them is getting a lot larger, a lot faster. Another one is doing it very slowly. compared to your standard graph. So that's kind of cool. In general, f of x equals c times a to the x. The point 0 c is the y-intercept. That's the takeaway. So notice how the y-intercept changed in all three of these cases, and it was all based off of what was being multiplied by your exponential function. All right, so the most important exponential function that we're going to talk about is natural exponential function. Most of the work that we do in this chapter with derivatives is going to have to do with e to the x. Now, if you're not used to looking at e, it's something that you should have at least had some passing knowledge of. But e is an irrational number. It does not matter to me if you know what the number is, but technically this is the definition. As n approaches infinity, e approaches 1 plus 1 for n to the nth power. If you're taking more calculus, this is probably something you'll want to focus on a little bit more. In graphing calculator, so this kind of tells you how you can find that, but our approximation for E is about 2.718. It's helpful if you can remember the approximation. Whether or not you remember this formal definition is probably not going to make a difference to you in this class, but the approximation is going to be really important to you because it kind of tells you that e to the x is going to look kind of close to 2 to the x. E is a really close base to 2. It's about 2.718. It's going to rise a little bit more rapidly because the base is larger, but it's going to have that same shape and it's going to follow that same behavior and look close to that graph. Now, as far as graphing the function, I'm going to graph the original, then we'll transform it. So the original one, I would say, is actually really important for us to get to know because when we're looking for critical numbers and finding derivatives and you're going to have to solve equations with exponentials, it's usually really helpful if you understand the behavior of the graph of the exponential function. So if I'm trying to graph just g of x equals e to the x, just use a couple of values here and then we'll work from there. So e to the negative 1 is going to occur when x equals negative 1. If you're not sure, put this in your calculator. I'm going to show you how. So your exponential button is second ln, and there you see that e to the x. That's how you're going to get the exponential to pop up. If you're going to be graphing this, negative 1, e to the negative first is about 0.368. 0.368. Now, e to the 0, well, if e is just some real numbered base, a real number to the 0 power is 1. And then e to the first is about 2.718. We just talked about that. If we can graph these 3 points, we can get a good general shape of the graph, and then we can transform that to get a graph of f. Okay, so if x is 0, y is 1, that's going to be our y-intercept. If x is 1, y is about 2.7-ish. And then if x is negative 1, we're about 0.3-ish. Do the best you can. You're just going to have to eyeball it. If you want to get a point for 2, that's fine. B will help to guide your graph. I'm going to just plug in e to the second power, and that's about 7.4-ish. 7.39-ish. Maybe we're going to be graphing it, so we can only get so close. So that happens at 2. Okay, so you're seeing the behavior of this graph go up. So this is our function g of x equals e to the x. And approaches the x-axis here, or y equals 0. Now we can use transformations to graph the graph of f. So what the transformations are doing here is you're going to shift right 2 units because we're subtracting inside the function. And then we're going to shift up 3 units. because we're adding outside of the function. So inside the function would be inside your x expression. Outside the function is just something that's happening outside of your variable expression. All right, so we're going to take our points. We're going to shift them to the right 2 and up 3. So if I'm going to the right 2, I'm going to start with my intercept. I'm going to go to the right 2 and up 3. So I'm now at 1. I'm going to add 3 more. I'm going to get up to 4. So this is where the intercept is moving. And then I'm going to take the point at -1 and about 0.368. I'm going to move it to the right 2. Sometimes I'm looking at this at a weird angle, and then I see it later, and I'm like, wow, this does not look anywhere near where we're supposed to be. All right, I'm going to take this point. I'm moving it to the right 2 and then up 3. Ish. Okay. I'm going to take the next point, which was 1, E, and I'm going to move it to the right 2. So 1, 2, and up 3. So 2.78 plus 3 is like 5.78, which is about right there. And if you feel like you have enough at this point to just make a general curve based off of this, that's fine. That's what your graph of f of x looks like. And we can always put in our calculators to check. But that would be my suggestion. Just get to know what E looks like. It's always going to have the same shape. If you're reflecting it, of course, that's going to change. But e to the x, I mean, the base is always going to be 2.718-ish. All right, what was I doing here? Oh, yes, doing this. Okay, so we'll graph both. So remember, E is second natural log, and then x. And then the other one was e to the x minus 2. And then outside of the function, so get out of your exponent, plus 3. And then we'll graph those. It's going to be a little bit harder to see f just because it's raised up a little bit higher, but we're going to see most of it. There it is. Pretty cool, right? It's hard to get students revved up and excited about exponential functions. We do what we can. Oh, wait, I have one more thing to say. Oh, you know what? No, this leads into the next page. Solving exponential equations. I do love this. Oh, anytime we get to solve equations is good. Now, you keep hearing me talk about derivatives and like one day we're going to have to do this. The whole point of reviewing this is so that we know how to work with exponential functions when we see them and when we're trying to find critical numbers and when we're trying to evaluate our expressions. We're going to need to solve sometimes some exponential equations. So I'm going to give you 2 of them that we're going to look at today. And then in the next section, when we talk about logarithms, we'll talk about using logs to solve exponential equations, which is really cool. All right, the first example, this is going to be 1/4 to the x equals 32 to the 3 minus x. Now we have some instructions here. We're going to see if the equation is of the form or easily put into the form e to the x equals b to the y. What that means is that b, your base, is the same on both sides. Now, what we're going to do is we're going to make the base the same on the both sides because it's something that we can easily do. So let's do that first. And then it says, otherwise start by isolating the exponent. We cannot do that in this case. We need to go ahead and equate our bases. So when I'm looking at 1/4, I was going to say 4. It's 1/4 and 32. I'm thinking about a number that they have in common. And I don't mean common factor, I mean common base. Now, if you're not very familiar with your exponential values, 2 to the 5th is 32. 2 squared is 4. So I'm thinking about using the number 2 as the common base. Okay, so 1/4 is 1 over 2 squared, which is 2 to the negative second power. And 32 is 2 to the 5th power. Once I have that information, I can now rewrite 1/4 and 32 as bases of 2. So that's something that you're just going to have to think about and see how you can get these to be equal to each other. But we're trying to get the same base on both sides if we have an equation that's of this form. So I'm going to rewrite this now as 2 to the negative second to the x equals 2 to the 5th to the 3 minus x. Notice that I put the parentheses on here because I want to make sure it's clear exactly what's happening on each side of the equation. Once we have the same base, what we're going to do is, let's see, where does it say to do this? Right. What we're going to be focusing on here is just number 1. Then you can set, oh, I needed to give you information. I was like, why is this missing in the notes? Because I'm supposed to write it for you. Okay, see if the equation is in the form or easily put in the form b to the x equals b to the y, then you can set the exponents equal to each other and solve. If the bases are the same, then the equation is the same on both sides if the exponents are also the same. So set x and what? So set x equal to y and solve for the variable. We have the same base. Now we need to equate the exponents. So I'm going to go ahead and do that now. And this maybe is an extraneous step, but I want you to see the step. So when you take a power to power, you multiply the powers. Be very careful when you do that on the right-hand side to put parentheses around the 3 minus x because it's 2 terms. And you want to make sure this 5 gets distributed into the parentheses. So the parentheses here are very important to you. Now that you have the same base, we can go ahead and set the exponents equal to each other. So I'm going to say same base, set exponents equal to each other, and solve. All right, so we have negative 2x equals 5 times 3 minus x. Negative 2x equals 15 minus 5x. Get your variable on one side, and whatever you don't need will move. Whatever you're not using will just stay. So I'm going to add 5x to both sides, and that leaves me with 3x equals 15. Divide both sides by 3, and you get x equals 5. Now, you can check this if you would like, but the idea here is that I can go back to the original equation. I can plug in 5 for the variable, and I should get the same thing on both sides. I'm even going to show you the check because why not? So this will be 1/4 to the 5th power, and we're trying to determine is that equal to 32 to the 3 minus 5 power. And if you're like, how would I know that? Well, you can put it into your calculator. That's fine. Why not? So don't forget your parentheses, however, 1/4 to the 5th. Now your calculator is going to give you this exponential notation. If it doesn't simplify it to a fraction for you, math, enter, then you'll have to do this by hand, but it does. So this is 1 over 1024. And then 32 to the 3 minus 5 power. I mean, we could just put a negative 2, but that's okay. Math, enter, is 1 over 1024. Check. They're the same. It's been a while since we've solved equations. I guess we solved a lot of linear equations in the last chapter, but those were boring. This is way cooler. Let's do one more, and then you are out of here. Example 2. 3 to the 2x power minus 12 times 3 to the x plus 27 equals 0. Okay, this is a little bit unconventional, but you have actually seen problems like this before. You just don't remember. Okay, one of the hardest things I think about this problem is just knowing where to start. This is actually quadratic in form. If that sounds familiar to you, you should have spent a lot of time, not a lot of time, but at least one section dealing with equations that were quadratic in form. So looking for a quantity squared plus a linear variation of that variable plus a constant. Notice that 3 to the 2x, I can write that as a square because by taking a power to a power, I multiply the powers. I can say that this is 3 to the x squared minus 12 times 3 to the x plus 27 equals 0. So it's not the most obvious thing, but I feel like by looking at this, you're like, okay, yeah, but it's so subtle that it's something that you would have to pull apart yourself and know to do. But it is quadratic in form, and now hopefully we can see that we have a variable term squared, a linear term kind of, and a constant term. So what we're going to do is we're going to do a little bit of a substitution here. You could technically solve this the way it is, but it's going to look confusing. So our trick is that we're going to let y be equal to 3 to the x. We're just going to do that so we can rewrite the equation so we don't have any exponential expressions left in it. So now we're going to say this is y squared minus 12y plus 27 equals 0. Now, as long as we've made this substitution, we know how to solve the quadratic equation. Remember, to solve the quadratic equation, we always want 0 on one side. So we have that. Try to solve it by factoring. You're looking for two numbers that multiply to 27 and add to negative 12. So I'm thinking negative 9 and negative 3. You can always use the quadratic formula. If you can solve it by factoring, it's going to be much easier to do that. All right, now solve this for y. So we know y equals 9 and y equals 3. And then when you get to the end, you're not done yet because you weren't actually asked to solve for y, you were asked to solve for x. So you're going to back substitute. Okay, so now I'm going to say that if y is 3 to the x, then it must be that 3 to the x equals 9 and 3 to the x equals 3. I think that at this point, you should be able to tell me what exponents x needs to be in both of these equations to make them true, but you can always go back and use example 1 to do that. I feel like we should be comfortable saying that it must be the case that x is 2 because 3 to the second power equals 9 and x equals 1 because 3 to the first power is 3. But what I was saying was technically you could just get the same base on both sides, just like we did in example 1, and equate the exponents. Like that. But if you feel like you can eyeball it, then eyeball it. It's not anything super complicated where I'd be like, oh, I wonder where they got that. Like, I know where you got that. You know what 3 squared is. Okay, so that's the kind of equation that you're going to be solving in this section. When we get into the next section talking about logarithms, then we're going to get into these instructions. And if you're looking at them and freaking out thinking that they look horrifying, it's not that bad. You've done it before. I'll just remind you of that. That's it for section 5.1. so you can get cracking on your homework and enjoy relearning and I don't know, all the things that you would do with exponential functions. Enjoy. Have a wonderful rest of your day.